Hello everyone and welcome to this unit on magnetism and electromagnetism. This is based on popular requests from students and the comments that I've been getting on YouTube. So I'll start with magnetism because the other part, which is electromagnetism, will not likely make sense to you unless you have a good grip on this chapter right here. So first off, let's just start with a simple categorization of materials related to this chapter of magnetism. And these materials can be broadly categorized into two, which is magnetic materials and non-magnetic materials. Pretty basic, right? Now, when we talk about non-magnetic materials, we basically mean that these materials are not magnets in itself, and they can also not be made into magnets. So a technical way of talking about this would be to say that these are not affected by a magnetic field, right? So even if they are placed in a magnetic field, this has no effect on them. So not affected by a magnetic field. If we talk about examples, so most, actually all non-metals would be non-magnetic materials. So examples would be something like silver, wood, brass, even copper for that matter, would be non-magnetic material. So these are some examples of non-magnetic materials. Now when we talk about magnetic materials, obviously these are ones which are affected by magnetic fields. And what is the matter? How are they affected? We'll be talking about that in a while. So these are affected by magnetic fields. Now magnetic materials in itself we can break down into two further categories, which is that we can say these can further be split into permanent, or what are also called hard magnetic materials, versus temporary or soft magnetic materials. Alright, so when we talk about permanent magnetic materials or hard magnetic materials, these are materials which are basically difficult to magnetize and demagnetize. So basically any magnet that you have, for example a horseshoe magnet or any other sort of magnet, for example like a bar magnet, all of these would be classified under the heading of permanent or hard magnetic materials because they are difficult to magnetize as well as difficult to demagnetize. So it's difficult to magnetize them once, but once you do that hard work on them, they retain that magnetism. It's very difficult to demagnetize them. So when we talk about permanent magnets, for example, all of the magnets that I just mentioned and more, all of these are made of steel. So this is the primary example of a permanent or a hard magnetic material. In comparison, when we talk about a temporary or soft magnetic material, these are materials which are easy to magnetize and demagnetize. Right, so it's very easy to magnetize them, but then they also lose their magnetism very quickly. A primary example of this is iron, also called soft iron. Now, how is magnetization and demagnetization actually achieved? We'll be talking about that in a while. But before that, let's just understand something related to what magnetic fields really are. So the concept of a magnetic field is this, that when we say we have a magnetic field, what does it really mean is that a magnetic field, like any other field, you must have studied gravitational fields and electric fields before this. So this is a region in space. And all fields are basically force fields. These are places, these are regions where a object would experience a force, but for every field, what makes it different, why do we even study these different types of fields, is because in each field, the property which causes it to experience a force is different. Now, for example, when you would have talked about gravitational fields, that's where a mass experiences a force. An electric field is where a charge experiences a force. So when we talk about a magnetic field, we say this is the region in space where a pole experiences a force. So this is what we mean when we say that a magnetic field exists. Right now, for example, me and you are also sitting in a magnetic field, and that's basically the magnetic field of the Earth. Now, the pole is basically the name of that magnetic particle because of which it experiences a force. Now, as we saw with mass, there's only one type of mass, right? So mass is just mass. But when we talk about charges, we have two types of charges, which is positive and negative. Similarly, with poles, there are two types of poles. There's the north, the N pole, and the south pole. Now it must also be, you must also know why we talk about two poles, is because when we talk about masses just attract each other all the time. Like any mass that I drop would fall towards the bottom, it would fall downwards towards the earth because earth attracts that mass. But for charges, why we talked about two types of charges is because some charges can attract, other charges can repel. Now with the North Pole and South Pole, it isn't like they came marked down from the sky with the North and South Poles marked. We introduced this because we know that some parts of a magnet attract, some parts of a magnet repel. This is what you also know if you have played with magnets like these. So with magnets, we know that some of these ends attempt to stick together, and then the other ends, basically if you try to bring them closer together, it seems an impossible task to do no matter how hard you try. So now this gives rise to basically a rule regarding magnets that we must remember. And again, that just came about from observation, is how we've marked the north and the south poles. What we say is this: it's pretty similar to what we said regarding the charges. We say that like poles would repel, and similarly, unlike poles are going to attract. Like means both poles are the same type, so north-north or south-south. And unlike means north-south or south-north. If I reverse the order, it doesn't make any difference to what I'm actually saying. So above, how we categorize the materials into permanent and temporary magnets was based off the ease of magnetization. So how easy or difficult it is to magnetize or demagnetize something. So the next thing that we are now talking about is how do you magnetize or demagnetize something. Now when we talk about demagnetization, that part is not in the syllabus anymore, which is that how you actually demagnetize something. There are different methods for it. For example, exposing it to high heat, hitting it with a hammer, and being subjecting it to a certain type of current, but it's not in this syllabus anymore. So how do you actually magnetize something? Let's talk about this. So basically there are just two ways of magnetizing something. One of these is called induced magnetism, and this is basically the idea that if we expose a temporary magnetic material to a permanent magnet, so poles are then induced in that temporary magnet and it becomes a magnet, right? So let me show you a video to illustrate how this works. First of all, the man places the magnet. So first of all, he places the nail close to the paper clips, but you see that the paper clips are not attracted to the nail as it was. This makes sense because we know that iron, this nail is made of iron. It's a temporary magnet and it needs magnetism to be induced in it. It needs to have that magnetism created in it for it to act as a magnet. And in this case, that magnetism is induced by this permanent magnet to which it has one of its ends attached. Now, one thing which is obvious here, but the examiner tests this very often, is this idea that induced magnetism is always attractive. So as you saw here, when we talked about the iron was also attracted to the magnet, and the nails were in turn attracted to, the clips were in turn attracted to the iron nail. So this is always attractive in nature. Now what this means is, for example, if I place a piece of iron near a bar magnet, which is a permanent magnet, it's always going to attract. But if I placed another magnet, so if I placed another magnet, those magnets could attract or repel based off which of these poles I'm making meet. If it's maybe a south-south pole that I'm making them meet with both of those souths matching up, then it could attract, then it could repel. If I make their north and south poles meet, they could attract. But if I place iron, then the iron is always going to be attracted to that magnet, right? This is a really important point. And the next one, the next method of magnetization, which we are going to talk about just briefly here, is by passing a DC current And how does this method work? Well, it's very straightforward. Let's say this is my iron core right here. Let me just make sure this is centered. And then around this is going to be wound some turns of wire. And this is connected to a battery, the circuit symbol of which looks like this. And with the terminals like this is positive, the longer one, the other one is negative. There's going to be current flowing into this. And the idea that we'll also talk about later in the chapter of electromagnetism is this, that because there's going to be a current in the solenoid here, this coil of wire is called a solenoid. It will also have a field set up around it, and pretty similarly to how we talked about it previously, because of that field, magnetism would also be induced or created into this iron core. Now, how do you find the direction of the magnetic field and whatnot? That we'll be talking about later. But this is another method of magnetizing a iron core. Now let's have a look at some of the past paper MCQs related to this, because we can't go on to structured questions right now. So this question is from Winter 22, paper 1-2, question number 29. Let's have a look at this one. As always, pause the video for a sec, have a look at this question and try it out on your own, and then press play again to see how I have solved this. Now this question says the north pole of a permanent magnet is placed in turn close to a piece of iron, the S pole of another magnet, and a piece of copper. Which objects are attracted to the north pole of the permanent magnet? So the piece of iron would basically be magnetized, would basically have magnetism induced in it, would have poles created in it when it comes within the field of a permanent magnet. So this would definitely be attracted. So it's this, and then base of this I can just tick off the entire row. And obviously, because unlike poles attract, the south pole would also be attracted, and the piece of copper, being a non-magnetic material, would not be affected at all. Let's go on to another question like this. So this question is summer 23, paper 1-1, question number 26. A student investigates a permanent magnet by suspending paper clips from the magnet as shown. Which statement is correct? Now we see the permanent magnet and we have the clips suspended from it. The only thing missing from the video here is a nail, so it's just directly connected, right? Which statement is correct? Each paper clip has a S pole at the top. So if there was an S pole at the top, then the south and south would repel, and we know this is not true, right? Basically, you know, because of induced magnetism, if this is a south, this must be a north pole so that they attract, and this must be south, and this must be north, and this must be south, and so on. So it's definitely not this. If the paper clips are made of soft iron, then they become demagnetized when the permanent magnet is removed. This is absolutely correct. This is what it means to be a temporary magnetic material, which is that they are only magnetized as long as that magnet is in there. Or for example, if they're placed in a solenoid, then only as long as the current is flowing. Why is C wrong? If the paper clips are made of steel, they become demagnetized when the permanent magnet is removed. This is wrong because steel is a hard or a permanent magnet, so it would stay magnetized for a pretty long period of time. More paper clips can be suspended from the North Pole. There is no such idea like this. Basically, if you're talking about a magnet, then both the poles are of equal strengths. So as many clips can be suspended from the south, an equal number can also be suspended from the north. And I've made a mistake quoting this reference. This is actually summer 19, paper 1-1, question 28. Let's go on to the next one. Now this question is the real summer 23, paper 1-1, question number 26. Let's have a look. A student uses a wooden clamp and a stand to hold a freely suspended bar magnet. The diagrams show that in experiment 1, the student holds a bar magnet next to the suspended magnet, then an iron bar next to the suspended magnet, and then the steel bar next to the suspended magnet. All of this is shown in these diagrams as well. In which experiments does the suspended magnet move? Now in the first one, you can see that there is a bar magnet which is suspended and another bar magnet is brought close in such a way that this south and north are going to attract because these are unlike poles. So this bar magnet would move. So the south and the north would move towards one another. So it's definitely going to move in this one. Next, if we talk about it with respect to the iron bar, with the iron bar also the magnets, the poles induced would be such that they cause attraction. So this would also be north-south, and in this case as well the magnet would move. For the steel bar, now the steel bar is also going to move. The steel bar is also going to have poles induced in it in the same way because induced magnetism is attractive, and in this case as well the suspended magnet would move towards here. So just something about experiment 1, even if these poles were reversed so that this south is here and this north is here, in that case as well the suspended magnet would move. The only difference this time is that because they are now going to repel, because like poles repel, then this would be moving away, but it would move nonetheless. So all of these are correct. So in all the experiments 1, 2 and 3, the suspended magnet moves. Let's go on to one last question. So this one is winter 21, paper 1-1, question number 27. Object X is on an electronic balance. Y is held above object X as shown. Reading on the balance increases when Y is moved towards X. Why does this happen? Now, if the reading here increases, that's basically because this is being pushed down more, because otherwise that was just measuring the weight of whatever this is. So now this is being pushed down more. This is only possible if both of these are repelling one another, because if one is pushing the other away, if Y is pushing X downwards, by Newton's third law, you can also say X pushes Y upwards. And this is only possible when both of these are magnets, because both of these are repelling one another. So both of these have to be magnets. If both of these were iron, there is going to be no change because both of these are temporary magnetic materials and none can influence the other in terms of magnetism. If Y is a magnet and X is made of iron, or if Y is made of iron and X is a magnet, in that case the materials would attract and this reading would reduce. So that's why it's going to be B. So that's something about magnetism. Now in the next couple of videos we'll be finishing up this chapter. So then we can move on to the more complicated ideas related to electromagnetism. See you there.